Hello, everyone. In this video, we extend our idea of linear transformations on Rn spaces to just general vector spaces. Luckily, practically everything we learned before is still true eventually, once you look at the process the right way. In fact, the definition is exactly the same. So a linear transformation is just mapping that goes from a vector space V to a vector space W in such a way that the linear transformation preserves linear combinations in the end. So we need two properties to have that be true. The transform of U plus V is equal to the transform of U plus the transform of V. That's the first one. And then the transform of C times U is C times the transform of U. Again, these are the properties we need to just preserve linear combination. So a linear combination in V, once you transform it, becomes a linear transformation in W, where the scalars are exactly the same. Of course, the vectors are different, but the scalars you use to form that linear combination are exactly the same. Now, you just need a couple examples. So let's define a mapping that goes from M sub nn to M sub nn. Remember, that's the set of all matrices of size n by n. And the mapping will be, take any matrix A and just give back its transpose. Now, I'm going to prove to you that that transformation is actually a linear one. To do so, the proof is very similar. And unfortunately, for the homework, they're all proofs this time. There's no computation to do. It's all verifying something is true. So to do so, you're going to follow this general process. So we'll take two vectors, in this case, matrices, in M sub nn, and just give me any scalar C. I have to show now the two properties are true that you see in the definition for linear transforms. The first one is, let's take the transform of A plus B. I will prove to you in the end that that is equal to the transform of A plus the transform of B. Well, the transform of any matrix is just the transpose of that matrix. So I then have A plus B transpose. But I remember, though, that the transpose distributes whose sums and differences. So that becomes the transpose of A plus the transform of B. But the transpose of A is the transformation of A, and the transpose of B is the transformation of B. So then we have the transformation of A plus B is the transformation of A plus the transformation of B. It's unfortunate that I have to say transpose and transformation at the same time, or at least quickly next to each other. I have to show that if you take the transformation of C times A, that it will be C times the transformation of A. So the transformation of C times A is the transpose of C times A. But scalars come in and out of the transpose operation. So that's C times the transpose of A, but that's C times the transformation of A. And therefore, by just those two properties, we get that T actually is a linear transformation. So let's just do it again. Another example. This time, let's define the differential operator D that'll go from the set of differentiable functions of first order. So we can at least take its first derivative and send it into just a set of functions. I don't care what the result is. And we'll just do the derivative like we always do. It's just the derivative of the function. I'm going to prove to you that D is a linear transformation. Actually, by doing so, this is just reiterating two properties of derivatives we already know. So as I did before, let's take two vectors in D. So that would then be two functions, f and g. And they have to be differentiable if they're going to be in the set D. And just choose C to be some scalar. Well, so then take the differential operator and apply it to the sum of the functions. That's equal to the derivative of the sum. But by properties of derivatives, the derivative of a sum is a sum of derivatives, but the derivative of f is d applied to f, and the derivative of g is just d applied to g. So that's the first. That means we just take the derivative of c times f, but by properties of derivatives, the derivative of a scalar multiple is a scalar multiple of derivatives. I can just take the scalar out and take the derivative of just f, but that's c times d applied to f. And that's the two properties we need to show that D is a linear transformation between these two vector spaces. I'll do one more. So then don't define the differential operator, just define an operator, t, that goes from R2 to the set of all polynomials. And it will take the vector AB and map it to the polynomial a minus bx squared plus 2ax cubed. Notice that the range of this operator is not the set of all polynomials, but that's okay. We don't care. It's just a mapping. I'm going to show you that this thing is a linear transformation. Now, there's a certain thing about transformations when it's applied to a vector from Rn. We tend to write them in column form, and we don't put parentheses around it, because otherwise we'd have parentheses and then brackets and then the numbers. It's hard to read. So we write it this way: the transformation bracket parentheses around the sum of two vectors. The sum of those two vectors, AB and CD, is the vector A plus C and D plus B. So then notice the first time I put parentheses around the sum because I have to, but the second one, I did not write parentheses around that one vector, A plus C and B plus D, because it'd be redundant and it'd be also hard to read. But by the transformation, this becomes that awful polynomial, just smashing up the formula. Remember, the form tells you how to map it. So then it says that whatever is here goes there and there. That's what I did. Whatever is here goes here and there. There we go. Next, I'm going to take that vector, because it's in P. I'm going to take that vector, and I'll make it be a sum of two vectors. One that has only A's and B's in it, and one that has only C's and D's in it. That's that. But the first polynomial I just wrote in parentheses, that is what T of AB is. And the second polynomial is T of CD. That's the first property to have a mapping be a linear transformation. Now I'll look at a transform applied to a scalar multiple of a vector AB. Well, a scalar multiple of the vector AB is the multiple applied to A and the multiple applied to B. But the transform of that vector, doing the same trick I just showed you, is this polynomial. Notice here, you can take that scalar K out. And by doing so, you then notice it's actually a scalar times, it's just the transform of the original vector. And that is the second and last property to call this particular transformation a linear transformation. That's it. This is how all the proofs are done. So there are two transformations that we give special names to. One is called the zero transformation. It's the transformation that sends every vector in V just to the zero vector in W. It's incredibly easy to show that's linear. I'm just proving not to do so. And there's another one called the identity transform that's defined on a single vector space. So it's a transformation that goes from the vector space back into it. And all it does is whatever the vector is, when you take the transform, the identity transform of that vector, you just get that vector back. That's called the identity transform. If I ever need to use multiple instances of the identity transform and on different vector spaces, I'll then use subscripts. So the identity transform on V would be I sub V. The identity transform on W would be I sub W. Okay. Now you have a basic idea of how to show that something is a linear transformation. The second thing to do is, well, if you have just a general mapping between two vector spaces, how can you show that it's not a linear transformation? That's actually really easy. That's actually easier than the other one. All you have to do is find two vectors or a scalar so that one of the two properties is just not true. Either show the transform of U plus V is not the transform of U plus the transform of V, or get some scalar in a vector. So the transform applied to a scalar times that U is just not equal to the scalar times the transform of U. Finding these things is called a counterexample. You just have to state U is this particular thing, V is this particular thing, and if you need the scalar is this particular thing. I'll give you two examples. So I want to convince you that this mapping from M22 to R is not a linear transformation. Now you need to remember what this means. M22 is a matrix. So in M22, there are entries in the first row, first column, second row, second column. That's what this here means. This transformation just takes a matrix, takes its entries on its main diagonal, and literally just multiplies them together. I have to convince you that that's not a linear transform. So the easiest way to do this usually, if it's not a linear transform, it usually is not a linear transform for lots of reasons. I would focus on basis vectors. So in M22, there's at least two vectors that will be useful for us. One would be the vector 1, 0, 0, 0, because notice T of that is going to be just 1 times 0, which is 0. And T of 0, 0, 0, 1, that is 0 times 1, that's also 0. But T of 1, 0, 0, 0 plus 0, 0, 0, 1, that would be then T of 1, 0, 0, 1, and that is 1 times 1, which is 1. So this is my counterexample. So T of 1, 0, 0, 0 plus 0, 0, 0, 1 is not equal to T applied to 1, 0, 0, 0 plus T of 0, 0, 0, 1. That's all I have to do. That violates the first property. So the second one, I have to show you that this mapping, it's a transform between spaces, but it's not a linear transform. So it says it takes a polynomial of degree 3 or less and sends it to be a polynomial of degree 3 or less. I have to show you that the mapping that takes a polynomial and then maps it to the same polynomial plus 1, that's not linear. Well, again, I can use almost anything. I'll look at the second property. So then notice if we define that the polynomial I have in mind would just be x, and I define c to be, let's say, I don't know, 2, then the transformation of 2 times x by definition is literally just 2x plus 1. But the transformation applied to just x is actually x plus 1. And T of 2x does not equal 2 times T of x. So it's not a linear transform because it violates the second property. And I believe that's enough for that video.